Hi, in this video, we're going to go over ways to evaluate our model when we're doing regression supervised learning. Okay, so when working on a real life project, either I want to make a predictive model, or maybe I'm trying to control situations such as, using a regression supervised learning model to control something along an assembly line, or maybe an experiment, something like that. Or maybe I'm using this for inference. Well, one thing I'm going to want to know on some level is like, how good of a model do I have? Can I trust this? Is this worthy of moving forward with? Or should I kick it to the curb? Now, typically when we're building predictive models, we're going to build a whole series of models. And what we're going to end up doing is that we're going to be using our metrics to decide which of our candidate models should actually go into production and which ones should we actually use for our actual purpose. All right, so now let's get into it. All right, so when we're doing supervised learning, and we're going to be focused on regression models, so we have like a numeric target variable that we're trying to predict. And so a good example of that is linear regression. It's critical that we evaluate how good or how poor is our model. The yeah, and something that's going to be important to us is that we want to check model quality on unseen data. That's going to be a mixture of our validation data and our test data. We're going to partition our data into our training data, our validation data, and our test data. Our training data is the data we use to build the model. Our validation data is our data that we're possibly do fine tuning on some model structures, but we'll use that to actually select which model will we actually put into production. And then our test data is our honest estimate of how the model will perform in the future. Now, a lot of times people will just do train and test. If I build a lot of models, there can be a shortcoming in that just by happenstance, the model I pick will look better than I really should trust it. And because of that, that's why we do the validation and test intermediate step. All right, so we're going to use metrics, specifically mean root square or mean squared error, root mean squared error, mean absolute error, to give us a quantitative measurement of our model's performance. And we'll also use visualizations to give a more qualitative aspect and a visual understanding of our model. By using both the metrics and the visualizations, we'll get a much better idea of the strengths and weaknesses of our models. The metrics and visualizations discussed here are not just indications of model fit. They can also provide insights into potential problems in the model, the nature of the errors it might be making, and suggest some things that we can do to correct things. We're going to walk through some common metrics and visualizations for this type of problem. And the data set that I'm working with is the house prices advanced regressions technique from Kaggle. All right, so of course, my first step is get my data going. In a previous video, I did my data prep. And so my target variable is sales price, and we're using the transformed version using the Yeo-Johnson transformation. Numeric missing values were imputed using the median, and numeric predictors were transformed using Yeo-Johnson and then centered scale to have mean 0, standard deviation 1. Categorical missing values were imputed with NA, which is a good choice because I'm making missing as a level in my data. And then I went ahead and I binned my categorical data into 3 levels of low, moderate, high. And so when it's high, those are the ones that had on average higher sales price. When it's low, on average, they had lower sales price for that level of the variable. So levels were grouped to have a similar conditional target variable average. And groups are also set to try and have approximately equal frequency of low, moderate, and high. And then the columns were converted over to dummy variables. Now, something about this, I mentioned that I used the Yeo-Johnson on the target variable. Well, when I run the model that I build off of this, what I would actually need to do before I can get my actual predicted sales price is I run the model. The model predicts the Yeo-Johnson version of the transformed version of sales price. We would have to do the inverse transformation on our predicted values before we actually get the sales price. And now when I load my data, you'll notice I use PyArrow. My understanding is that PyArrow is much faster than the default setting. And also something that you'll notice I do is I have a pretty big dictionary set up here to load my data. All right, so if I don't have this dictionary set up when I load a CSV, Python or Pandas is going to go through and try to figure out what each column is. Well, if I have something like social security numbers, then, and there's no hyphens or anything like that, then, Pandas is going to think, hey, this is a number. And it would make sense to have addition, subtraction, and I could lose leading zeros. So this is bad. So I want to stay as a string. All right, and so you'll notice that my ID column is a string here. Also, this will speed up loading time because it doesn't have to go through the process of figuring out how to interpret what's going on. It'll go, hey, this is a float, boom, grab it, and let's roll. And you see there are quite a few columns. And you'll notice that here is an example of that, like fence had low or moderate levels for binning, while roof style had low, moderate, and high. And these are dummy variables that I'm highlighting right now. And so here we know that at least one of these had a pretty large chunk, larger than a third of all the observations. All right, so now let's go ahead and grab our actual training data. And so there's a column called train tests in the data that indicates what partition is in, training, validation, test. And so here I'm going to just take my training data and my, so here these are the predictors columns, and this is the target variable. And now I want to do feature selection. Now, the best way to do feature selection is always to go in and work through and use subject matter knowledge, and to also like use a mixture of like metrics such as association analysis, correlation, stuff like that. But you can see that there are quite a few columns. This YouTube video does not justify slugging through all this. So what I'm going to do, I'm going to go ahead and do feature selection using a model. The Lasso model structure is a regression model structure that will actually do feature selection for us. What this does, this will assign a coefficient of 0 for features that we want to exclude from our model. Now, I'm still going to use regular old linear regression because that's just like a good default setting. But here I'm just using this for the moment to talk about or to do my feature selection. Now, there's a problem with automated feature selection when I've got dummy variables. Remember that I have low, moderate, and high dummy variables for each categorical predictor variable. Well, what's going to end up happening is that Lasso doesn't know, doesn't consider, doesn't care about keeping these three levels together. And so what's likely going to happen is that some of them are going to get kicked out. And instead of having three levels I had before, maybe I'll have just one or two. And there could be a problem for your project if your stakeholders want to have all levels included. I've been in that situation. After doing automated feature selection, I've gone in and included the levels that were kicked out. That's personally how I've handled that. I'm not going to worry about that here. Specifically, if there's a two-level categorical predictor variable, kicking one out is actually the way we want to do it. That way, it's just one binary column. All right, so here I'm going to use Lasso cross-validation. Here I'm going to put in the random state of 823. That is part of the telephone number for all telephones at the University of Central Florida. Increase the maximum iterations to make sure it goes through. And then what I'm going to do is I'm going to go across all the cross-validations. And if it was kept one or more times in one of the models, I'm going to keep it here. It's just a first initial go. And so now so here I'm saying, hey, I only want to have it where the coefficients are not 0. I'm taking the average. So if it has an average across all cross validations, not 0, which more than likely, very, very likely that things are not going to cancel out on me. So this is grabbing just the ones I want to keep. Every time that I have a predictor variable that has 0 for coefficient every single time, it's getting kicked out. Don't have to worry about it. All right, and so now I am going to keep all the features I actually want in a list. And so you'll notice that in this process, I would have, like this is manually put in there. I ran the code, grabbed what I wanted, and put it in there. And so now here is a little bit different. So this is actually how I got the original, this list here was originally grabbed using this code. Now, because of some random aspects, this might be a little bit different than what I put here. And actually there is a little bit of difference, like lot frontage is first, while lot area is over here. So there's a little bit of a difference. But for this purpose, for this video, it's okay. All right, so now let's go ahead and take our linear regression model. So I'm using vanilla linear regression, and I'm going to just fit the model. And then what I'm going to do, I'm going to get the predicted values. Why am I getting the predicted values? Because I want to evaluate model performance. Now, there are ways to have things automatically computed for you, but when we start doing the train validation test split, usually we have to get a little bit more hands-on and more manual in our calculations. And that's how I'm going to do things here. So what I'm doing here, I'm fitting the linear regression model on my training data. Now I'm taking that model and I'm predicting the value for each row in my data set, regardless of its train validation or test. And now what I'm going to do, I'm going to set up a data frame, and the index is going to be train validation test to store what the results are going to be so that I can look at. So first one we're going to look at is mean absolute error. All right, the mean absolute error, we can say that as the average error. I like using this to articulate to my stakeholders. I feel like mean squared error or root mean squared error is actually the better metric to use, better loss function. But mean absolute error is the average error. It's easier to talk to people just about, here's the average error, boom. Now, when I say average, I mean, if it's too small or too big, we're taking of a prediction. So if predicted low or predicted high, I'm taking the absolute value regardless, and then I'm taking the average. So that's why it's the mean absolute error. Typically speaking, if I was to not do the absolute value and I took the average, most models, the average will be really close to 0. It's not really that informative to take the average. All right, so here I'm just going to take the absolute difference between the predicted value and the actual. You can see that here, there's the difference between predicted and actual absolute value, take the average. And so now we can see that we got 0.2 for training, 0.25 for validation, and 0.27 for test. Okay. Typically, you're going to see that the training statistic is going to most of the time be the best. So we want as little error as possible. That means we want the smallest mean absolute error. And our training metric tends to be optimistic. Why is that? Because the model was fit on that data. The whole scheme is to get the best fitting model I can on the data I give it. Therefore, when I go and I do my metrics using the training data, I'm going to get an optimistic number. Now, here we have our validation data and our test data. If I see a gap, that's between training, validation, or train and test, that's an indication I have overfitting. All right, so here, I think I have just a touch of overfitting. I take the point of view that all models overfit on their training data. It's a good point of view. It's a good way to approach predictive modeling. All models overfit on their training data. And so here, I might want to consider removing a few predictor variables. All right, so now let's keep on going. Let's go with mean squared error. So this is the mean of the squared difference between the predicted values and the actuals as a loss function. So when I put this into the training function to fit the model, as a loss function, the mean squared error does a better job avoiding the big errors than mean absolute error. As a loss function, the mean squared error will have a larger average absolute error than the mean absolute error most of the time. When I have like numbers that are, when predicted values are like 0.5, 0.4, 0.3, typically when like negative 0.2, if my target variables values are really close to 0, then like within -1 to 1, then my mean absolute error will probably be a little bit bigger. But for most situations, we're going to have our mean squared error will be a larger larger value when we compare. Now here I'm just running through a for loop to get this, and you'll notice I've got 0.2 and 0.08, 0.25, 0.12, 0.27, 0.14. All right, so why is it that the mean squared error is just doing better, just smaller? Well, that's because the actual linear regression model is fine-tuned to minimize the mean squared error. So the entire fitting process was designed to minimize the mean squared error. So here it's going to be a little bit smaller. Now, if I was to change my loss function, we would see usually mean absolute error will be smaller. All right, now root mean squared error, this is just the square root of the mean squared error. Now, why do we want this? Well, if let's say my predicted value is in feet, okay, then my residuals, my errors will be in feet. When I take my mean squared error though, my mean squared error will be in feet squared. That's a different unit. So it's harder to compare to the original value. If I take the square root, I put it on the same unit of measurement as my actual original data. And so here, most of the time we want root mean squared error. Minimizing root mean squared error is equivalent to minimizing mean squared error. Simple thing from calculus to show that. And so, yeah, the advantage here is that we have the same unit. The mean absolute error is automatically on the same unit as the target variable also. And so this is a little bit, closer to like mean absolute error in a way. And you can see that I've got 0.28, 0.35, 0.37, and you'll notice that every single time training, validation, and test are in order. All right, so now let's talk about correlation. So here I'm going to take the correlation between my predicted value and the actual value. And of course, I want to split this up by my partition data. And so we can see that on my training, we have 0.96, we have 0.94, and 0.92 as the correlation. Very good correlations. Now, on this metric, if this is not a huge correlation, you have a junk model. Just to let you know. All right, so I'm actually gonna state that here. I'll right in front of you. All right, so if the correlation is not close to 1, you have a junk model. Model is attempting to predict the target variable. All right, now the coefficient of determination, we can use this to address like how much variation in one variable is accounted for by another. So this is a useful one. This is Pearson's correlation, by the way. A lot of times for predictor variables, if I have a non-linear regression situation or I'm doing a more exotic modeling structure, I'll use Spearman's correlation for predictor variables target. But when I'm working with target variable and predicted value, that every single time is going to be Pearson's correlation, which is the default. That's the one that's the most well understood, the one you see almost always. Now, the next one is to visualize the target variable by the predicted variable with a scatter plot. And so first thing I want to point out is that you'll notice that our target variable is on a scale of -4 to 4 approximately. And the reason for that is, remember, we took sales price of a house, applied Yo-Johnson, and then subtracted the mean of the Yo-Johnson divided by the standard deviation of the Yo-Johnson transformation. And so here we can see that most of the things are going to be between -3 and 3. That was the whole goal of Yo-Johnson. Now the scatter plot, we want this to look like y equals x, that straight line where if I go -3 to 3, -2 to 2 is a point, -1, 1, 0, 0, and so on. If I go along here, that is the line I want to see. I want to see everything tight on that line. And, so that's the training data. Here's our validation data, scatter plot. And here's our test set. And you'll notice that it works out the test set isn't as tight as the others. Huh. Now, next one is one that I use at work, Vigentile plots. What we're trying to do here, we're trying to look at how well does our model perform by regions of the target variable. So for Vigentile, that's 20. I'm going to break up the target variable values into 20 approximately equal bins. And then I'm going to take the average of the target variable in each bin, take the average of the predicted value in each bin, and then I'm going to do a scatter plot to check to see how things are going. All right, now here's for the training. And so the predicted value is in like that orange, and the sales price is in blue. And so one thing that you'll notice is that there's always, in these plots, it's hard for the extreme values to get picked up. Our models at the very, very largest target variable values and the least target variable values, it's hard for our models to pick that up. So expect to see a gap to the far left and far right. It's a question of how much is that gap. And so each of these points, so this is the first bin of the target variable values, take the average of the target variable, that is the blue point, take the corresponding average of the predicted value for the same observation, that is this X. And then we can trace along each of the Vigentiles. And almost guaranteed, not 100% guaranteed, but almost guaranteed, you'll see that the far left, far right predicted values are going to be less extreme. Now, these are averages over each of the bins. There's 20 bins. And so what we use this for is to try and decide, hey, are there any regions where our model isn't performing as well? Maybe there's something going on with our data. We want to know, maybe if it's like a really extreme looking value, maybe we should try a different model possibly if things didn't work out. So here in the 6th bin, we can see that there's a little bit of a gap. And this 13th bin, there's a little bit of a gap. Notice that Python always starts at 0. I hate that. Now for our validation data, we can see that it's a little bit less tight. It's still pretty close, but it's not quite. We can see that in this region here, these two bins, our model is over predicting. And we see that it's under predicting on the far right, over predicting on the far left, pretty close otherwise though. And it's a little bit more wiggly when we get to the test set. And honestly, this is not surprising given what we've already seen. We would expect the Vigentile plot to be the worst. Now, something about this, it can work out. I have a very, very low accuracy model, and because of the averaging in these bins, these dots can be like right on top of each other. I've had that experience where I've had a very, very inaccurate model that had crazy variance that averaged out that the points were just right on top of the predicted value average, or that predicted value averages were right on top of the bin averages. And so because of the averaging, you can't really trust this as an accuracy evaluation. The ones that we looked at previously are better suited for that. This is for us to say, hey, are there regions in the target variable where our model is not performing as well as we would like? All right, so we talked about metrics for evaluating our model. All right, so we talked about mean absolute error, that is our average error. We talked about mean squared error. Mean squared error is, we're working to minimize the squared error, the average of the squared error. And so that squared error as a loss function is a better choice if I want to avoid big errors. The mean absolute error is better for a loss function if I'm okay with errors being evenly throughout, and it's okay for a few of them to get like spiky and get bigger. We also talked about root mean squared error. We talked about the scatter plot of a predicted with the target variable value, and we talked about the Vigentile plots. With all of these, we're going to take the training data, validation data, and test data, and whichever metrics we're using, whichever visualizations we're using, we're going to do all three. And if I see a big difference between training and validation or training and test, that's an indication I have overfitting. Here, I think we have a little bit of overfitting. And overfitting happens on all models. Take the point of view that all models overfit. It's just to what degree. If I'm concerned with overfitting on a simple linear regression model, really my only choice is to use a different model structure or to kick out a few predictor variables. The more predictor variables I have, the more prone to overfitting I am. All right, well, that's all I've got for you. Life is short, do math.